Welcome to an example that shows how to take a short series and express it using sigma notation, also called summation notation. Before I start, I'd first like to look at some common non-arithmetic and non-geometric sequences. Here are some common sequences that are neither arithmetic nor geometric. The first of which is the squared numbers. And each of these sequences starts at n equals 1. So for example, you might notice that the first number is 1 squared, the second number is 2 squared, the third number is 3 squared, and so on and so forth, 4 squared, 5 squared, 6 squared. So this sequence can be written using the explicit formula a sub n equals n squared, where n starts at 1. Down here we have the perfect cubes. You may notice, starting at n equals 1 again, that this is nothing more than the number 1 cubed. 8 can be thought of as 2 cubed. 27 can be thought as 3 cubed. So the explicit formula a sub n equals n cubed would give this sequence when you start at n equals 1. This would be what you'd get at n equals 2. This is what you'd get at n equals 3, and so on and so forth. The last one, called an alternating sequence because it alternates negative, positive, negative, positive, can be obtained by taking the base of -1 and either raising to an odd power or an even power. In mathematics, if you take the number -1 and you raise to an odd number, the result is a -1. And if you take -1 and raise to an even power, the result is +1. So look what happens when you start at n equals 1. That would be the first term. And then you plug in n equals 2 for the second term, n equals 3 for the third term, etc. Plugging n equals 1 into this formula, you'd have -1 raised to the first power, which is indeed -1. Replacing n with the number 2 would give -1 squared, and -1 squared is +1, and notice that this is an even power, and the result is 1. Because n goes odd, even, our results will alternate between -1, 1, -1, 1. That being said, let's go back. The intent of the examples is not to have you recognize a pattern, as we've already done that. The intent of the example is to show that even though I can recognize the numbers in this series as being a subset of the numbers in the sequences just shown in the video, for example 4, 9, 16, and 25 are perfect squares, and that 27, 64, 125, and 216 is part of our perfect cube list. So the intent isn't to recognize the pattern. We already have the pattern. The intent is to show you how to use sigma notation and adjust the formula for the fact that the numbers in the numerators start in the middle of the pattern. In fact, it starts at n equals 2. And the denominators, our perfect cubes, start in the perfect cube pattern at n equals 3. So we must adjust the formulas to accommodate this series. So for example, normally my numerator could be written as n squared. The problem is I want to write my formula so that n starts at 1. If you start n with 1, replacing n with 1 would give 1 squared, or 1, and we want it to be the case when someone replaces n with 1, they get 4 in the numerator. We'll worry about the denominator in a minute. So if I'm forcing the issue that you start n with 1, we need it so that when someone replaces n with 1, it's the equivalent of replacing n with 2 in this formula. So what I'm going to do is change the expression n squared slightly so that when someone replaces n with 1, it's the equivalent of replacing n with 2 in this sequence. All I have to do, since we're starting n with 1, and I'd rather them start at 2, is to simply add 1. So here's the normal equation. So all I did was take this expression and replace n with n plus 1. Now, when someone replaces n with 1, my base won't be 1. It'll be 1 plus 1, or 2 squared. And 2 squared is 4. Moreover, when someone replaces n with 2, hopefully they get the second term in my sequence, or at least the numerator in my second term, of 9. And they will. When someone replaces n with 2, they will get 2 plus 1 quantity squared, which is 3 squared, which is 9. This isn't the only way you could do the problem. In fact, there's infinitely many ways you can do the problem. This is just one. the one where I insist that n starts at 1. Now, for the denominator, because the numbers in my denominator appear to be a subset of the perfect cubes, I would like to write n cubed. The problem with this is when someone replaces n with 1, they're going to get 1 cubed or 1 in the denominator, and we want it so that when someone replaces n with 1, they get 27. So let's go down here and have a look at how these numbers are generated. Perfect cubes are such that the first number can be thought of as 1 cubed. The second term can be thought of as 2 cubed. The third term, the one we actually want to start with here, can be thought of as 3 cubed. So we want it so that when someone replaces n with 1, they don't get 1 cubed. We want them to get 3 cubed. So starting at n equals 1, how can I get them to have a base of 3? When n is 1, we want the denominator to be 3 cubed. So having an n there, replacing n with 1 gives 1. We want it to be a 3, so what I will do is simply add 2. I will keep the exponent of 3 here. Now, rather than plugging in 1 and getting 1 cubed, replacing n with 1 will give me a base of 3, like I wanted, because I added 2 in the parentheses. Replacing n with 1 gives 1 plus 2 or 3, and of course it's being cubed. You can check further. This is what happens when n is 1. To check what happens when n is 2, hopefully when n is 2, I will get out 64 because that's my second term of my series. When n is 2, replacing n with 2 here would be 2 plus 2 cubed, which is 4 cubed, which is what we want. 4 cubed is 64, and we get 64. So in summary, normally we'd put an n here, but because we're starting at 1, and we would rather start at n equals 3, I compensated by adding 2. Now when someone replaces n with 1, because I've added 2, it'll start in the third term of this sequence. And don't forget these are the perfect cube numbers, so I need to cube this. Because this is a series and we need to sum the numbers up, we will use a capital Greek letter sigma that represents summation. And we will tell people that n starts at 1. And to tell people that there are 4 numbers that we want to end the series when they replace n with 4, we will put a 4 up here. This is one of many ways to do this problem. Let's do another example. Notice in this example all my numerators are 1, but it alternates in sign. Positive, negative, positive, negative, positive. Well, we have a sequence for which we wrote an explicit formula that alternated in sign. The one we had shown in this video starts at negative 1, not positive 1. So we were going to have to adjust our formula accordingly. Also, my denominator is perfect squared numbers, but it does not start with the first perfect square in this sequence. In fact, it starts at the 5th. So let's start at least with the alternating sign. Normally, with alternating sign, we would write negative 1 to the n, and you could leave it like that depending on when you want to start n with. But if you want to force things so that n starts with 1, then when someone replaces n with 1, they'll get negative 1, and then replacing n with 1 would give to the first power. They're going to get negative 1, and we want the series to start with positive 1. So to compensate, if you remember, whenever n is odd, you get a negative. When n is even, you get a positive. Since I want my exponent to be even, because I want it to be the case when someone replaces n with 1, that they get a result of positive 1, not negative 1. One way to compensate for this is to get people, by plugging in an odd number, to make my exponent even by simply adding or subtracting 1. If I add 1, then when someone replaces n with 1, they would get negative 1 to the 1 plus 1, and that would be negative 1 squared, which would be positive 1. So it turns out this would generate that alternating pattern where you start with a positive and then it'll alternate negative, positive, negative, positive, etc. In my denominator, again starting at n with 1, we need to start the perfect squared list at 25. Meaning, normally, this is what we would have at n equals 5 if you were to use this formula. 5 squared is 25. But we're starting our summation notation at 1. So we need to make it so that someone replaces n with 1, it's as if they're replacing n with 5. So I can do this by simply adding 4. And then remember, these are the squared numbers, so we need to square that. Now, when someone replaces n with 1, because I've added 4, that'll make the base 5. As a quick check, replacing n with 1, my denominator would be 1 plus 4 quantity squared, which is 5 squared, which is 25. So I replaced n with 1, and I got 1/25, as we should. At the end, this would be n equals 2, n equals 3, n equals 4, n equals 5. So we need to end at n equals 5. When someone replaces n with 5, just as a check, they would get negative 1 to the 5 plus 1. In the denominator, replacing n with 5 would be 5 plus 4 squared. So I'm not writing out the whole series, I'm just writing out what this expression would be at n equals 5. So having replaced this n with 5 and that n with 5, notice I get negative 1 to the 6th power. That would be negative 1 to an even power, which gives me 1. This is nothing more than 9 squared, which is 81. So replacing n with 5, I end with 1 over 81. Just to show a variety of examples to show you this is not the only way to do the problem. I did the problem this way because I said I want to start n with 1. If you're the writer of the mathematics, you can choose to do things how you want. So for example, let me show you another way where I don't necessitate that n starts with 1. So for example, one of the hang-ups in our problem is that we started the squared numbers at 25. That would be, in the normal sequence of squared numbers, the 5th term. So what you could do is, rather than changing the expression, you could leave it n squared, and then just tell people to start at n equals 5. So if you're doing it that way, starting at n equals 5, we need to get the numerator to be positive 1 again, so we still would have to augment this. If you just wrote negative 1 to the n, that wouldn't work out in this case, because 5 is an odd number, and negative 1 to the 5th power would be negative 1, and we wanted to start out at positive 1. So again, you could change the exponent from an odd power to even by either adding 1 or subtracting 1. So if I put a plus 1 here, when someone replaces n with 5, my exponent will actually be 6, which is even, and negative 1 to an even power would give me positive 1. So you can check to see when someone replaces n with 5 in this expression, they would indeed get 1 over 25. But having started n at 5, this term would be which someone gets at n equals 6, 7, this would be 8, this would be 9, so we would have to end our problem at n equals 9. So it turns out that even though these two different ways of writing the answer look a lot different than one another, they actually both generate the exact same series. Hopefully this was a good introduction to writing series using sigma or what's called summation notation.